All right, everyone, welcome to the next lecture. This one, we're going to be talking about carrier motion, and we're going to get introduced to junctions. So far in the class, we have looked at sort of how the semiconductor is structured and how the energy bands work out. So we've learned sort of where the electrons or the carriers, electrons and holes, where the carriers are located, but we haven't talked about where they move and how they move. So hopefully we're going to clear that up with this lecture here. So there are three main ways that a carrier is going to move. There's Brownian motion, diffusion, and drift. Now, hopefully you've covered some of these in some capacity in some of your previous classes. If not, that's okay. We aren't going to get super deep into the math for most of these. The concepts should do just fine. So we'll start with Brownian motion. So Brownian motion is what happens if you have like a perfect crystal that, or it's like uniformly doped, like it's a very uniform system that is under no external influence whatsoever. All right, so you can imagine this being like a perfect crystal of silicon out in space somewhere. So we know that even though there's no external influence, there's internal influence, right? So we have thermal energy. All right, so we know from like some of our previous courses that there's thermal energy going around. So the electrons aren't just sitting still. They're sort of like bouncing around, moving, they're vibrating, the nuclei are vibrating, all this kind of stuff. So things are moving, but because it's completely uniform and there's no force on it to direct it to go one way or another, they are going to move randomly. So this is one of the things that like Einstein sort of came up with, wrote a paper on like what, 1905, like won a Nobel Prize for it, I think. So it's really important, and the math can be rather complicated. But essentially all you need to know is that if the carrier is left alone to its own devices and it has some thermal energy, it'll wiggle around in a random that is, or in a direction that is entirely random. It'll be completely stochastic, and it'll have kinetic energy or average kinetic energy of 3/2 kT. And you can get that from like StatMech. Recall that it's actually like a Boltzmann distribution of like energy, or yeah, it's like a number of particles with that energy, and then there's like the energy, and it'll kind of go sort of like this, just like black body radiation, where there will be a whole bunch of particles that have a little bit less than the average. I think the average is like actually right around there, but the peak is just before that. There's going to be a whole bunch that have higher than that energy. There's going to be a bunch that have lower energy than that, but on average, they'll have like a certain amount of energy, and they're just moving around. So they're going to keep moving in their chosen random direction, just like this. We can imagine we have this system of 4 particles, and they're just going to keep moving in whichever direction they're going because there's no external forces, so there's no reason for them to change direction. But then they can scatter. They can like hit something. There's a lot of different types of scattering that can happen. I have sort of glossed over it. If you want to look at some of the types of scattering, if you look at, I think it's PowerPoint lecture 3 and 4 on sunlight on the 140A page on our group server, has some discussions of the different types of scattering that can happen, and also your textbook PRA, which again, if you have a copy of that, that's great. If you don't, it's very cheap. Or if you want an online version, send me an email. So what will happen is that you can imagine these just being like billiard balls going around a pool table, and eventually they'll just hit the side and they'll bounce off, right? So maybe this electron is scattering off of a nucleus or another electron, because there's going to be this idea of a mean free path and a mean free time, which means that the average amount of distance and the average amount of time, respectively, that one of these particles, one of these carriers can move without scattering off of something. But once that happens, it'll change direction, most likely. That's kind of what scattering means. So it's going to change direction, which again will be random. And so it'll change direction and everything will get a new random direction. But all in all, you get these random walk paths. So if you were to average out all of the motion of all of the carriers in the entire semiconductor, you'll get that like the net distance covered is 0. There will, or infinitesimally tiny. It should be 0 though, theoretically. That they'll just continue to scatter all around and just keep hitting stuff and just not ever really move from where they started. So that's Brownian motion. That's going on all the time in like every system, semiconductors included. But as you can probably figure out, it's not the most interesting for us. This is just sort of good to know that it's there, but it doesn't really help us in understanding how these things are actually moving around. So the next thing is diffusion. So now we're going to imagine we still have this semiconductor that's like out in space, not being affected by anything. But now it's not going to have a random distribution of carriers. So there will be more electrons on one side than the other. Or maybe now we have sort of a system where now our semiconductor is in contact with something else that has, say, like a different carrier concentration. So maybe we bring it in contact with like a solution or another semiconductor or something that has a different concentration of carriers. Well, that'll cause diffusion to happen. And diffusion happens due to concentration gradients. And it's very similar, actually. It builds on the concepts from Brownian motion. And we can get into some of the math here. Now, if you wanted to see a full derivation of diffusion and like the diffusion equations and Fick's laws and all these kinds of things, again, check your textbook. It goes through some of that. It can be really complicated, but the basic idea can be understood with these pictures here. So if we imagine our semiconductor, and we have a non-uniform concentration of holes, which is what we're looking at here in this graph. We're saying that there are more holes over here than there are over here. And we're just using holes arbitrarily. We could do this with electrons too. It works out the same. So what we're going to look at, we're going to say, all right, there's more holes on this side than this side. And we want to say, okay, if I look at my semiconductor here, and I imagine that there's this like plane A in the middle, I want to know how many of my particles, how many of my carriers are going to pass through this region in a given amount of time. We're going to assume this amount of time is like the mean free time, right? So how many are going to go through this way and how many are going to go through the other way? So recall, if we're thinking about Brownian motion, you would expect those to be equivalent. You would expect that in a given time, an equal number of electrons would go to the right as go to the left. But now, because we have a concentration gradient, you can think about it, say like we have like a box, right? And I've got a couple of vibrating spheres over here. And then they all get to go in a random direction. Well, let's say this one goes over here, and this one's going to go over there, and this one's here, and there, there, and there, right? So going randomly. But then if you look on this side, none of them are doing anything. And you can see that the mean free time, or that the time before scattering, if the electron is going this way, is going to be different than if the electron is going, say, this way. So these electrons can get farther in a similar amount of time. So they can get farther before they scatter off of something. So we're going to kind of average it out for our actual math here. But this is sort of the idea that they can get farther. There's more available space for them. And if you were to like let this go over and over and over again until you reach equilibrium, eventually it's going to be completely equally populated by these spheres, and it'll average out to Brownian motion again, where there'll be just sort of random walks. Everything is nice and uniform. So that's sort of the system we're thinking about. So we have more electrons on one side than the other, so it's going to be easier for them to go from one side to the other because they're going to like scatter less. The concentration gradient is going to help out as well. So the question we're going to ask, like I said before, is how many holes in the volume, negative L times the area of this plane, and positive L of times the area of the plane will cross that spot in a given time. And we can take the time to be arbitrary, but we'll say in the mean free time. So what we're saying is if this is x equals 0 right there, we're going to say this is negative L right there, and this is going to be positive L. So how many electrons on this side are going to go past this barrier? And how many electrons on this side are going to go past the barrier, right? Okay, so the way we're going to figure that out is with this equation here. We're going to say that the number of holes that go forward, let's say we're going to say positive L is forward, is going to be equal to the area of our plane divided by 2 multiplied by the integral of the number of holes, so our hole concentration. With respect to x, we're just going to do one direction here, from negative L to 0, right? Which makes sense. We're going to essentially integrate this graph over here. Then we're going to do the same thing for the reverse to get a similar equation. So you're going to do area over 2. And now this time we're going to go from 0 to positive L. But we're, again, just integrating that equation. And then you do like a ton of math. Like I said, this gets pretty mathy pretty fast. It's not something that's really important for this class. You just need to sort of understand the basic concept. But if that's something that really helps, let me know. We can do a derivation, but it's not that important. You need to know how we start and how we end. So what we end up with is an equation for what we call the diffusion current density. So generally, if you see I, that means current, and J is current density, which is usually current divided by area. So that's what that is. So we have this diffusion current. So the current caused by our carriers diffusing across that barrier is, and in this case, we're looking at just the p-type, so we're just looking at holes, is equal to the negative fundamental charge multiplied by VRMS, which is the root mean squared velocity, which you can get from the thermal energy and statistical mechanics, multiplied by L, which is your distance, divided by 2. And then you multiply that by the derivative of the carrier concentration with respect to x. So that's in one dimension. So then we're going to simplify this even more. We are going to combine all of these things, because we can say that for a given temperature, that's a constant. So we are going to introduce the concept of a diffusion coefficient, which is going to be defined as the root mean squared velocity multiplied by the path, by the length we're interested in, divided by 2, which we will then also generalize to 3D, because here we were only looking at dp dx, but remember we're looking at volumes here, so we need to look at all 3 directions. And we can get the final equation, which is that the diffusion current is going to be equal to the negative of the fundamental charge multiplied by the diffusion coefficient for holes in this system and the gradient of our carrier concentration in the system. A similar thing can be shown for electrons or for n-type carriers. Just note that you get rid of that minus sign. So let's look here. So if we want to look at our how our equation changes with different parameters, if let's say we increase the temperature, right? We're going to bump up the temperature of our system. That is going to increase the root mean squared velocity, which means it's going to increase our d value. And thus, so with temperature, so as T increases, J diff increases. Remember, note that this minus sign is just saying that whether it's conventional or electronic current. So that's all we're doing there is we're just swapping the sign. The magnitude will be larger. The magnitude of the current is going to be larger. Similarly, if we increase the concentration gradient, so if instead of this sort of, we have this P of X, we had sort of like this nice graph here. If we instead had a pretty severe concentration gradient like this, that's also going to increase your diffusion current. Though notice then, similarly, if our concentration gradient decreases, in fact, becomes 0. So if we had a uniform motion, the diffusion current becomes 0, right? Which is what we'd expect. So that's good. So we'll write down as the gradient increases, J diff increases. Cool? All right. So now the last type of motion that's important for us is drift. So drift is now saying that we have our semiconductor, and this time let's assume that it's evenly doped. We don't have a carrier concentration. We don't have a concentration gradient here because it'll just make our lives a little bit easier. But what we do have is an external force. In particular, we're going to have an electric field. So we have Brownian motion, which is motion due to thermal energy, and it's completely random. We have diffusion, which is motion due to carrier concentrations or concentration gradients, and is not random, it's directional. And then we have drift, which is carrier motion through due to the influence of an electric field, and that is also directional. So it is when they're under the influence of an electric field. So we can say, we have our particle over here doing its nice little random walk. There's maybe it could be diffusing. It doesn't really matter, but like it's just moving around however it is it wants to move. And then all of a sudden we're going to push it really hard with this electric field. You don't have to push it really hard. The drift current could be rather small. But you could just imagine that this could be either a very tiny effect or completely overwhelming. And it'll be extremely important when dealing with junctions and dealing with how semiconductors actually operate. So this is a pretty important concept. So let's do some math. So let's recall that applying a voltage to our system is the same thing as creating an electric field. So if you apply a potential of 1 volt across your sample that's like a centimeter long, you could calculate like how strong that electric field is in between the two contacts, which are applying the voltage. Because that's all that a voltage is. It's a change in potential energy, which changes in potential energy because you have a field there, right? And we'll get into a little bit more. We'll get into some graphs and things that might help with that. But that's what's causing this. We're changing the potential energy landscape. So then we could argue that the drift current is equivalent to the charge that will pass through a given area A, just like we said before, in the given time t, assuming that the carriers have a given velocity, which we're going to say is Vd, or the drift velocity. So we have a similar setup as before, but now we have an electric field. We have our same sliver of area A, and we're going to say the current is equivalent to the fundamental charge, right? Because we have to convert from that. In this case, we're doing conventional current, so we're going to look at the concentration of holes. If you wanted to do electrical current, you're going to flip that. You're going to make this a minus, and you're going to make that N. Times the speed at which they go and the area, right? So we want to say how many carriers per second. We're going to say, or how much charge per second. We're going to say this is going to be charge per carrier. This is number of carriers. And this is the speed, velocity, but like how fast they're moving. And then this is the area of interest. All right, because if we increase the area, there's going to be more carriers, so there will be a higher current. But notice if we divide by the area, we get the current density, which does not change with area because it's normalized with area. So that's why chemists tend to like to use current density, because it's more generalizable and it can help you kind of like get rid of any effects from the area of your electrode. But current can work just fine. So, okay, let's switch over to current density because we're happier doing that. And now we're going to, instead of saying that this velocity is just a given number, it's going to be just a scalar, we're going to turn it into a vector. We now get this equation here, that the drift current density is going to be equal to fundamental charge times number of carriers times the drift velocity vector. Okay. But we want to relate the current density not to like the velocity of our species or like the carrier constant. Like we want to relate it to the electric field strength, right? Because that's what drift is it's current versus electric field strength. So let's do that. So we're going to use the relationship that the drift velocity is going to be equal to the mobility of the carriers, which is this mu factor here, times the electric field. Now that's all that the mobility is. The mobility is just a proportionality constant that is used to relate the drift velocity and the electric field. So if, for example, I apply an electric field of 1 volt per centimeter, and the particles are moving at 10 meters per second, you can then calculate out like, okay, that means that the mobility is equal to whatever that is, right? So that's how we interrelate between the two. So now we have our drift current density in terms of some fundamental constants that are easy to either measure or calculate, right? It can be difficult to measure what the actual velocity of the carriers are in like a normal experimental setup. But usually the mobility is known. It's usually a tabulated value, so we don't have to worry about that. And the electric field we can calculate. We know we can figure that out pretty easily. So now our drift current density is going to be equal to this here. So fundamental charge, our mobility, concentration of carriers times our electric field. Right? Note that we do not change sign here because the electric field is going to like affect how the electrons move, right? Because if we have an electric field here and we put an electron here, so that's an E minus, that's going to go this way. And if we put a hole, that's going to go this way. Right, so the directions are going to reverse, which we should account with like mobility, with the mobilities and stuff, I think. At least it wasn't the sign wasn't changed in the textbook, so I think we're cool there. If it comes up, I'll let you know. All right. Now, okay. So those are the equations governing drift and diffusion. Because we talked Brownian motion, there are equations, we don't care about them. For diffusion, we care. These are things like Fick's laws, but really it's due to these concentration gradients is what we're interested in. And we know that if we increase the concentration gradient, the drift current increases. If we decrease it, it decreases. Drift current is also going to be important. And if we note here, if we increase the mobility, the drift current increases, but more notably, if we either increase the concentration of our carriers or if we increase the strength of our electric field, the drift current will increase, right? So we have a positive relationship between drift current and electric field, and a positive relationship between the drift current and our concentration gradient. Okay, cool. So that's going to be important in building a junction, because now we have a concept of the different ways our carriers can move and the equations that are governing them. So let's put it to the test. So we're going to say, I'm going to assume we have semiconductor X, which is an intrinsic semiconductor and has the energies that I've drawn below. So we have our conduction band, Fermi level, and valence band. All right. Fermi level, I'm always going to draw with a dashed line because, again, it's not a real energy level. It's a chemical potential. There is not necessarily anything there. Our conduction band is just here. Valence band is down there. And then this line here is going to be my interface. Right now, there's nothing touching it, so there's nothing there. It's just a vacuum, but that'll be important. So this line here is an interface. All right, so now let's put our semiconductor X in contact with something. So from our previous examples, we can sort of think about, all right, what kind of motion would we expect from putting it in contact with something? So we're going to put it in contact with, let's say, a solution with some species R, some chemical species that has an infinite concentration or an effectively infinite concentration, and a chemical potential that is in between our valence band and Fermi level. So ER, the energy of R, is going to be between the valence band and the Fermi level. Or graphically, it'll look like this. All right, so now we have our E of R that is in contact with our semiconductor. Notice that it's actually touching the interface there. All right, so what happens? Well, let's think about that. We've seen before that this Fermi level acts as a chemical potential and will determine whether or not you're actually going to transfer electrons or accept electrons. And we know that if this is intrinsic, we've got like some electrons up here and some holes up here. And so compared to our species R, we have a higher Fermi level, which means that we have a higher potential, or rather a higher energy, and we have an excess of electrons, right? So it's going to be easy to take our electrons and give them to R. Or if you want to think about it this way, they're coming from the conduction band, right? So that's what's going to happen. We're going to start transferring electrons to R. But how are we transferring them, right? Well, there is an excess of electrons on one side of our equation, right? So there, you can think about this as like concentration of electrons with respect to X. So we have more electrons on this side, right? So what's going to happen? We're going to start having them diffuse over. Because right now there's no electric field, no nothing. The only thing that's going to cause these carriers to move is a concentration gradient. So that's what they're going to do. So we're going to have diffusion start to kick in. All right, so they're going to start to diffuse across the interface and reduce our species R. So just like before, we see our electrons pop over. I like to draw the electrons as coming from the Fermi level because it helps with chemical intuition. Just remember that, in fact, they're coming from up there. And on a microscopic level, so this is macroscopic. This is saying like as a system, what's going on. But microscopically, what's happening is that we have our atoms of X. And really, like, this would be ionized already, and this electron is sort of free floating. But it helps to think about it this way, where you are taking an electron from species X and you are going to give it to R. And that results in a net positive charge on the side of our semiconductor and a net negative charge on the side of our solution. Now, because R is functionally infinite in concentration, we're going to assume that reducing it doesn't actually change its potential very much. We're just going to say there's so much R that we can reduce it forever and never change the fact that there's going to be a state there. And we're also going to assume that the reduced form of R is completely non-reactive and it just goes away. Okay, so now that we have a positive potential on one side of the interface and a negative potential on the other side of the interface, we start to induce an electric field. So there is now an electric field pointing out of our semiconductor towards our solution. So as this field builds up, we get drift. So not only do we get drift that opposes our diffusion current, right? So if we look on this side, right? So our diffusion current is what's bringing the electron over here. But now because we have our electric field here, remember the electron will go in the opposite direction of the vector for our electric field. So that's going to want to pull electrons back. All right, so our electric field is opposing that diffusion force. All right. So for a while, diffusion will be stronger because there's still a large concentration gradient. There's going to be a higher potential energy on one side than the other. But remember, when we add in drift, when we add in that electric field, we are modifying the potential energy landscape. And so as we continue to put electrons over that barrier, or over that interface, the drift current and the electric field gets stronger and stronger. And the way that it happens is we are going to have, let's say this is the charge density. So this is going to be like some, Q over volume. It'll sort of max out, and we'll get it as to why it is like a square like this in the next lecture. But just take my word for it for now, that over some width, some thickness of our semiconductor, we get a charge buildup as we're transferring charges. And it sort of makes sense that like it's going to be easier to transfer charge from a species that's at the surface than one that's way into the bulk. Remember when we were looking at like why photosynthesis has like these different steps down in order to move our electrons and holes away? It's because it's really, really hard to transfer electrons at a really far distance. So it's easier to do it when you're closer. So there's some distance over which we're going to get like a whole bunch of charge. When you do that, you can then say, okay, well then what's the electric field strength at any given point? Well, as you get closer and closer to the interface, the electric field gets stronger and stronger and stronger until you get to a maximum value right at the interface, which makes sense, right? Because we're like getting past more and more and more positive charges in this case. So you can imagine, think about it like this way. So we have a whole bunch of positive charges. So you could imagine if I was like living over here, I'm really feeling influence mostly from these two, right? Especially if we assume that there's like some negative charges over here that keep this electric field being fairly linear. But then if I'm over here, now I've got 4 positive charges behind me. So the electric field's going to be stronger, right? So that's the idea there. The electric field gets stronger and stronger and stronger, which causes the electric potential or the voltage to kind of do this, right? You can like, it causes this like increase, this like kind of shift up in the electric potential up to a maximum right at the interface. Again, look, see how this is all occurring in this same sort of region that we're going to call W for now. Some width of the semiconductor. Okay, so we have moved charges through diffusion, and we're starting to move charges via drift. And as we keep getting more and more charges across the interface, the drift gets stronger and stronger and stronger, and this electric field, this V max, gets bigger and bigger and bigger until things really start to change. So as you remember, as you change the potential energy landscape, what you're doing is you are moving the bands, because these bands are bands of energy, right? This right there, that's an energy band. That's saying that anything on that level will have this much potential energy. So in this case, this much like electrical potential energy. But now we're saying that we are changing what that looks like. We are going to alter the potential energy landscape. And in this case, what's going to happen is our band is going to be pulled down so that an electron in the bulk will now have a slightly lower potential energy than it did before. And there is now a barrier introduced for electrons and holes to move around if they wanted to go to the right. And this sort of helps understand why the diffusion, why the drift is opposing diffusion, because now as I'm pulling this band down further and further and further, I'm making it harder and harder for an electron to overcome this barrier and actually make it across the interface. And you keep doing this, in fact, until your Fermi level comes down. Note that the Fermi level doesn't like bend. It actually just moves. The Fermi level does not bend. It moves, at least in this case. So it's going to shift until the Fermi levels have equaled each other. And because, remember, our E of R is, we're going to assume the concentration of that is massive, so we're not significantly affecting the concentration. We're saying that the energy of R is just staying still. There's too many species of R that are around for us to actually affect how many of them there are and how much energy they have. So we're going to say like that's just staying still. But our semiconductor doesn't have infinite charges, and so as it starts to move around, that's where that potential is going to change. And this makes sense that they would equal each other out, right? Because we want to get to equilibrium. And in equilibrium, there's going to be no net motion of charges, right? So if we want to get a system that is not having a net transfer of charge, the chemical potentials of those two systems have to be equal. So eventually, our Fermi level will be equal to the energy of our species in solution. And at this point, drift and diffusion have canceled each other out. So in this, once we hit this, J drift is equal to, really it's negative J diffusion. Right, they're equal and opposite to each other. And that results in a system that looks like this. And you notice that the bands are not straight anymore. They have bent in response, and they bent in response to the electric field that is now present at the interface, right? Because we've transferred a whole bunch of charges. So there's a whole bunch of positive charges over here and a whole bunch of negative charges over here. And that electric field is what's bending this stuff. And that's what's causing all of these effects. And we refer to a diagram that looks like this as a band bending diagram, which makes sense, right? It's just a diagram that shows how the bands bend. And they are going to be super important going forward. We're going to look at all sorts of different junctions, different types of junctions, different chemical applications, and the band bending diagram will help us make sense out of all of it. But at this point, we've constructed a junction and we sort of understand why they happen. So in summary, we have looked at different types of carrier motion. We looked at Brownian motion, we looked at diffusion, and we looked at drift. And they're all important, but probably the two most important for us are diffusion and drift. We looked at their equations. We saw how they relate to different parameters, different physical parameters. And then we sort of constructed a junction using this. We sort of said, all right, we know that these concepts should work. We know how the system in principle should behave. And doing that, we can put two things together and say, aha, this must be how a junction works. So in the next lecture, we're going to get really in depth into different junctions and different types of junctions. We're going to start to like put numbers into things and hopefully get a much better understanding of why these are important. So I'll see you in the next lecture.